Alright, so today I'm going to be explaining resonance in RLC circuits. In order to do this, I'm going to explain a little bit about what an RLC circuit is. Here we have a picture of an RLC circuit, which is basically just a circuit with a resistor represented by the letter R, an inductor represented by the letter L, and a capacitor represented by the letter C, all in series. And there's an AC current that is flowing through this. Something important to know is that these are all things that impede current. However, their resistances do not add. You can't just add them. That's why I'm going to explain a little bit about something called impedance, um, which is the combined effect of resistance, inductive resistance, and capacitive resistance. Um, this can be found with the equation listed right here, which is the peak current represented by I naught, equal to our peak source voltage divided by our impedance of current. Something important to know is the greater the impedance, the smaller the current. And conservation of charge requires that current to be the same in each part of the circuit at all times, so that we can say the currents in R, L, and C are all equal in phase. We know that the voltage across the inductor, VL, leads the current by 1/4 of a cycle. The voltage across the capacitor, which is VC, follows the current by 1/4 of a cycle, and the voltage across the resistor, which is VR, is exactly in phase with the current. And V is the total voltage around the circuit. According to Kirchhoff's loop rule, the total voltage around the circuit, which is V, is also the voltage source. And basically, based off of what I just said, the voltage across the inductor, which is VL, and the voltage across the capacitor, which is VC, are both 180 degrees apart from each other, which will come important later. But it basically means that they can essentially cancel each other out. And we need to know that peak voltages don't align, meaning that the peak voltage of the source does not equal the peak voltages of R, L, and C. However, there's an equation that can show the relationship, which is the equation listed here at the bottom left. And we have this equation which shows the relationship between the peak voltage of the source and the peak voltages across R, L, and C. And so if we use Ohm's law and some definitions for reactance, inductive, and capacitance, we can do some substituting for our variables and get a new equation. This equation is the impedance of an RLC series AC circuit. And so now that we understand a little bit more about impedance, we can go and we take Ohm's law and the expression for impedance, which are the two equations at the top, Ohm's law on the left and the expression for impedance on the right. And when we combine the two, we substitute in the expression for impedance into Ohm's law. This is the equation that we get. And we know that these reactances will vary with frequency. And here we have a graph which shows the reactances, both the inductive and the capacitive, with respect to frequency. The capacitive reactance is inversely proportional to the frequency, and the inductive reactance is directly proportional, which means that at some point for a given circuit, those two values will be equal to each other. This occurs where those two lines intersect, and this means that the inductive and the conductive reactances are equal, which means that they'll essentially cancel each other out. We can find this intermediate frequency by taking the XL equal to XC equation at the top there and substituting the definitions for those two and then we solve for f naught, and this will give us the equation that we need to find the resonant frequency. This is the natural frequency at which the circuit would oscillate if not driven by a voltage source. And resonant frequencies are used in radios, as the receiver of a radio is an RLC circuit that oscillates best at its resonant frequency, or its f naught, and this can help the radio to be able to receive a desired frequency and reject others, so it can be selective of its frequencies at that point.